Good morning, my lovely 13s. Right, buddies, here we are starting a brand new mechanics unit. I think this isn't as bad as the last one. You guys are... I like this unit, but I mean, I think that it's not as hard as the last one. Because you guys were really, really good at those ladder questions with moments and forces and equilibrium and stuff like that. That's actually probably, if I'm honest, the toughest thing that you'll have to do this year. So that's behind you now, which is great. And we're starting our brand new unit, which is called Projectile Motions, or Projectile Motion. But before we get started, my buddies, put just a little brief title. It's a bit of a starter. Kinematics Quick Review. Okay? So what we have to think about, my buddies, is I think you haven't done this yet this year. No, you definitely haven't. We got to remember some SUVAT from last year, my buddies, before we get started. And SUVAT and like why things move, or not why things move, but how things move, is called kinematics. So first things first is you don't have to memorize the SUVAT equations anymore, but you should. You don't have to. They're in the formula book. And here they all are. If you want to jot them down, that's cool. If you don't want to, that's cool as well. Now, SUVAT equations, my buddies, are just pretty much, well, they're 5 different equations, each one with one of the SUVAT letters eliminated. So in this one here, v equals u plus at, you can see that it's not got s in it. So if ever you had a question that you were after v but you didn't know s, this would be your one to look at. So I hope that you remember how SUVAT goes. Yeah, I hope you remember how SUVAT goes. If you'd like, you can tell me as well, and I'll give you a really hard revision of it, but I think you'll be good at it, and you're just going to have to try to match up with my method when we go ahead and do them. Cool beans, buddies? SUVAT equations. They're for constant acceleration, okay? If something is at constant acceleration... Oh, and one other. If something's at constant velocity, you know how there's SUVAT? You guys remember SUT as well, right? Now, that one is for constant speed. Constant, I'm going to call it velocity, though. Okay, that one is for constant velocity, yeah? SUVAT is for constant acceleration, SUT is for constant velocity, and that's just distance equals speed times time. Cool. So, as a bit of a starter, here we go, my buddies. It says, Mr. Wade is seeking vengeance against a group of students who didn't do their homework on time. He stands on top of the 15-meter history stairs and plans to drop a water balloon on the unsuspecting students. If the students are walking in their group at constant speed, so SUT, of 1.5 kilometers per hour, for how far away, so how far away from the target should the balloon be before, or how far should they be before Mr. Wade drops the balloon in order to hit them? Right, buddies. So this is a standard question, but it's a 2-part one. It's a tricky one from year 12, but it shouldn't be too tricky for you. I'm going to write, I think, on either side of this because I've made these slides so I can write on the board, because these are not special. These are like my offline slides, but that's okay. Okay, so let's do it. Here we go. We have 2 parts of this thing, okay? First things first is we have the balloon, okay? The balloon has got its own motion, okay? We also have the students who have their own motion as well. And they, my lovelies, yeah, we've got them as well. Now, first things first, when you look at this question is I instantly say there's a problem in that the speed is given in kilometers per hour. Now, it's always a good idea in physics and in mechanics, because this is physics, it's always a good idea to use standard units when you can, because if you put standard units in, you get standard units out. So instead of kilometers per hour, which isn't in keeping with meters and seconds and so on, we'll switch this to meters per second. So do you guys remember what you do to switch kilometers per hour to meters per second? That's right, my buddies. You divide by 3.6. Now the reason why is because there is 1,000 meters in a kilometer, so that's the factor of 1,000 in. But there's also 3,600 seconds per hour. So 3,600 divided by 1,000 is 3.6. That's where that comes from. So it's not mysterious. But instantly, let's spin off that stupid 1.5. We'll go 1.5 divided by 3.6. We'll get 5/12, which I'm going to use as a decimal because we're physicists now, don't forget. 0.417. 0.417 meters per second. So you don't have to use exact form because whilst you are in a maths lesson, this is a physics topic. Cool beans? Sweet. Right then. So let's think about the balloon's motion. Well, first things first, the balloon starts here and it falls down, okay? let's just write down what we know about it. And here's what you do for every single question. Number 1, define a direction to be positive. The balloon is falling down, so I'm definitely going to have down as positive. What do you do next? You write suvat. Okay, that's unskippable. I want you to write suvat every single question. And you go through and you write in things that you know. Displacement, S. Do we know what that is? Well, yeah, 15 meters, the question says. U, the initial speed. Do we know the speed with which I dropped the balloon? Even though I'm the meme teacher. Yeah, do we know the speed? Well, yeah, it's 0 because it's not being thrown down, it's being dropped. V, the final speed, the speed with which it hits the kids' heads. Well, no, we don't know that. It is actually the speed the instant before it meets the kids' heads, so it's not 0. And the acceleration. Well, yeah, it's 9.8 meters per second squared, because don't forget, that's the acceleration due to gravity. The time, do we know that? Well, no. Okay. Now, which of these things are going to be useful if the question, our end question, is to figure out, well, how far away the kids should be when you drop the balloon? Well, here's what we're going to look at. Look at the kids. The kids have sut. So they're not suvat, they're sut. Ooh, and I should have said left is positive. I'm going to erase it just to make this perfect. Left is positive, okay, because that's the way that they're walking. And here we go. Sut, not suvat. It's sut because there's no acceleration. They're walking at constant speed. Do we know how far away the kids are walking? Or do we know how far they're going to walk? Well, no. Do we know their speed? Well, yeah, we do actually. 0.417 meters per second is their speed. Do we know how long? No. How long they're going to walk for? No. What do I want to figure out now? I've laid out the balloon, I've laid out the kids. What do I need to do? That's it, buddies. You've got it. If I can figure out the time it takes for the balloon to fall, then that means I can figure out that I need to drop it that many seconds before the kids arrive. If I know how many seconds I have to drop before the kids arrive, I can figure out from the students how far I can figure out from them then how far away they'd have to be before I drop it. Cool beans, buddies? You draw a square around the question mark that you don't know the answer to. That's how I do it anyway, and that's how you should do it too. Okay, so here we go, buddies. I'm after t, I don't have v, so which equation is it? Well, up to your suvat equations, you'll have found it's s equals ut plus 1/2 at squared. You should write the formula. You should also write the substitution. 15 equals, u is just 0, so I'm going to lazily just pop a 0 in, plus 1/2 9.8 t squared. Okay, so this is good to practice putting this in, and there's your first method mark there, okay? So we've already got a method mark, and there's never a method mark for workings out, so if you want, just skip every step and just tell me what t is. That's what I would do anyway, because there's no method mark for that. You guys are year 13, so I trust that your rearranging skills are good. So here we go. It's going to be 15 divided by, open bracket, 0.5 times 9.8. Yep, equals that. Square root of that answer equals, and I've got 1.75 seconds to 3 sig fig. Okay, so oops, and that means it's going to take 1.75 seconds for the balloon to fall, which means I should drop the balloon 1.75 seconds before the kids arrive. So how do I get how far away they should be? Well, it's constant speed, this one. This is like speed equals distance over time. Or in physics, sut, s equals ut. That's distance equals speed times time, which is the same. Which means the distance is just this, 0.417 times 1.75. No units in the substitutions, okay? Because you've already addressed the standard units in your givens, and this is why it's so good to lay it out my way. While it might look like it's extra steps, it's not. I'm time saving you big time here. 0.417 times 1.75 equals 0.73. No, let's do more. 0.7. Oh, it is 0.730 with the rounded numbers. So pretty much I should drop the balloon 73 centimeters before where the kids are actually going to arrive. So I hope that's okay, and I hope that that counts as a good warm-up for you for suvat. Okay, now quickly then, the next topic that we're actually going to do today, new this year, is called projectile motion. Now, I love teaching this in person, but I'll see you again soon, hopefully, and then I'll be able to do some demonstrations with you to show it. But projectile motion is the title. Now, projectile motion is just throwing something, okay? Or shooting a cannon out of a cannon, or shooting a bullet out of a gun, or throwing a basketball, or kicking a football, or dropping something. It's all well, maybe not dropping something, but yeah, anything that's been given a bit of oomph and let go out of your hand and let to work under gravity is projectile motion, okay? So just to show you how it works is going to be this. It's got a really important fact. So I've got a football that's been kicked up and it's going down, okay? So that's what this is just a picture of. It's unsurprising. It's made a big parabolic arc, which we'll learn about soon. Okay, now there's something important to notice. So I'm just going to consider the ball's motion in two different directions, in vertical and horizontal. So here we go. To start with, what you're going to find is when it's kicked up initially, it's going to have a good whack of speed going upward and a good whack of speed going forward, okay? So they've kicked it for distance, let's say. Cool. Now, in the next frame, as it goes up, is it going as fast or is it going slower upward? Well, yes, slower. So I'm going to draw the arrow a bit shorter. Now, what about its speed across? Is it the same, faster, slower? Well, certainly not faster because it doesn't have an engine on it or anything, and probably not really slower. So it will have air resistance on it, but at kind of slow speeds that we get in a football in the small amount of time that it's in the space, it's almost that it's going to be you're going to get that the air resistance is pretty much negligible, and that's actually an okay assumption. So whilst there is air resistance for the speed of a football and the length of time it's in the air, incorporating it isn't going to actually affect our result too much. Now, air resistance would be really important. For instance, if you were flying a spaceship back to Earth, entering the atmosphere, air resistance would be totally important there, but because it would rip up in the atmosphere, but for football it's not too important. Okay, next thing then, my buddies. Next frame. It's going to be a little bit slower still, but this is going to be the same. Next one here, slower still, but this is going to be the same. Next one here, it's not got any speed at all. It's just going to be going across. So all the acrosses stay the same the entire time, and what you find is only the acceleration vertically changes, okay? It's only vertically does the speed change. Cool, cool, cool. Now, here we go then, buddies. Scrolling swiftly down, let's check it out. This is a really cool clip. I can't show it to you right now because I want to make your video quick, but if you type in Mythbusters bullet being fired, or if you're really geeky and you want to type that in exactly, it's quite a useful thing to see. You won't believe me, but this means, because only the vertical speed changes, if you were to take a gun and point it out horizontally and shoot a bullet, which goes so quick, right? Like super fast bullet speed. If you were to shoot a bullet out of a gun, what you're going to find is actually if someone were to drop a bullet beside the gun at the same speed that you shot it out horizontally, the dropped bullet and the shot bullet will actually land on the ground at the exact same time, okay? And that's cool. It's because the acceleration is only vertical. So dropping a bullet is going to be the same as shooting it out of a gun, provided that the gun was horizontal, because the gun only adds a horizontal speed, not a vertical speed. So dropping a bullet is actually going to hit the ground at the same time as shooting one, which I think is which I think is amazing. It's really, really cool, and this video demonstrates it for you. So if you want to watch that video, that's cool. Here's the takeaway from it. For all projectiles, horizontal velocity remains constant, but there's acceleration due to gravity in the vertical. So that's essentially the long and short of this entire unit. So boom, I've taught you an entire unit. Not really though, because I'm going to have to show you it in a lot more detail. So happy days. Little note there. Okay, sweet. And the actual final topic that we're going to do today is this. Title is Objects Projected Horizontally. Cool, cool, cool. Now, here we go. We've got this. You decide to be adventurous and jump from a 10-meter tall cliff into the deep water below. You get off to a running start and jump horizontally, so you've not leapt into the air as somebody actually would. You've just kind of run off the edge like there's something wrong with you. You didn't actually jump off the cliff, you ran off the edge. Now, here you go, my buddies. Question is, how long will it take for you to hit the water to start with? Okay. Before I even do that, I really like this picture of this person jumping because it lends itself really well to all the stuff that we've learned. So people's center of mass is like there in their middle, on blokes it's about there, okay? So if you check it out, this bloke, even though he's spinning, can be represented by a dot. Can you see that? So his center of mass doesn't change throughout all of this rubbish. And anyway, I just really like this picture. So he's falling down, but can you see that the distance between the blue dots, so kind of ignore the bloke's body, but the distance between the blue dots horizontally is about the same. So if I was to measure from there to there, that's the same distance as measuring from there to there, which is the same distance as measuring from there to there. See what I mean? Horizontally, do you get me? These distances between the gaps stay the same in every single frame. And that proves what I just told you, my buddies, that since these green bars are all about the same, it proves what we just said, that the vertical speed stays the same. Or, sorry, the horizontal speed stays the same. Now, that's not true of the vertical speed, because look, from his body from there to there, it's only that long. But if you look at this frame, it's like that long. The green line got way bigger. See what I mean? So, left to right, they stay the same. Vertically, they don't. Anyway, happy days. Let's try it. Okay, so first ever projectile question. Where will I write this? I'm going to zoom out, and I'm going to write in the margins again. Here we go. Right. For part A, it says, how long will it take you to hit the water? Okay. What should you do, buddies? Well, I would say a question like this probably should have a bit of a photo, or a picture, I should say. So let's draw a bit of a picture. Here we go. Boom, boom, boom. It's just a cliff. Okay? Here's our kid that's going to be jumping off the edge. There he is. And if you look at him, what's he doing to start with? Well, he's jumping off the edge from a running speed of 4.5 meters per second. Okay? The cliff itself was 10 meters tall, so that's given as well. And his path is going to be like this. He's going to go doot, 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 until he splashes down in the water below. Cool beans, that's a good representation of what's happening? Okay. How long does it take for you to hit the water? Here's the question you've got to ask yourself in all of these. How long? If it's how long, are we dealing horizontally or vertically? Which is going to tell us how long? That's right, vertical. So you ready? Here we go. Vert. Define a direction to be positive. Either's fine. I'm going to go with down because all the motion is down. Now, once you've got that, what are you going to do? Well, you're going to write out your suvat. So you ready? Suvat. Suvat. And here we go. S, do we know the distance that he's in the air for? And we're only carrying vertically. Or the distance, yeah. It's 10 meters. The initial speed, U, is it 4.5? Well, no, actually. It's 0 meters per second. It's 0 because this speed was completely horizontal. His vertical speed was not when he jumped off, so we don't know that. V, don't know. Acceleration, we do know that. 9.8 meters per second squared. Positive because down's positive. And time, do we know that? Nope, but it's what we desire. So we need the suvat that's not got V in it. Which one is it? Yeah, it's probably the most common one. It's the S equals UT plus 1/2 AT squared. Cool. Whack your numbers in. 10 equals 0 plus 1/2 9.8 t squared. No marks for rearranging, so t equals 10 divided by 0.5 times 9. Oops. 0.5 times 9.8 equals that, square root. And this equals 1.43 seconds to 3 significant figures. Happy days. Got it, my buddies? 1.43 seconds is how long he's in the air for. Sweet. On to B. For B, it says, how far from the cliff face will you be when you enter the water? So in B, it's actually asking for this distance here. It wants to know how long that is. Well, are we dealing horizontally or vertically now? Well, yeah, horizontally. So you write down this. You write hor. You pick a direction to be positive. Right, because all the motion is right. That's a sensible direction. And then what do you write down? Is it suvat or is it sut? Well, yeah, it's sut. Cool. Do we know the distance? Well, no, that's what we want. And a square around it. U, the initial speed. This time it is 4.5 meters per second. T, the time that he's in the air for, well, we got that from the previous, 1.43 seconds. So what do we get? Well, we get S equals UT, which means S equals 4.5, 1.43, which means the distance is 1.43 times 4.5. It's going to be 6.44 meters, 6.44 meters to 3 sig fig. I used rounded answers there, so I might not be quite in keeping with you. Cool beans? Sweet. And here we go, the final one. I think what I'm going to do is I'm going to skip C, and I'll let you try C, because I don't want this video to take for ages. I want you to try this, so I'll do D with you, but I want you to try this one. But for D, let's do D together. Okay, for D, it says this. It says, what velocity, including direction, will you have 1.43 seconds after your jump? Okay, that's asking this, buddies. 1.43 seconds, as you know, is when you're hitting the water from part A. Okay, so it's there. It wants to know the velocity, including direction, that you'll have after your jump. So, which means you'll be having some speed horizontally and some speed vertically. So your velocity is going to be something like that when you hit the water. Maybe not as steep as that, but your velocity is going to be into the water, both downward and to the right. So here we go. First things first is we got to know two things. Do we know our horizontal velocity when we're hitting the water? Well, yeah, actually we do. Because the horizontal velocity remains the same throughout. Whether you're here at the start, or here, halfway, or here, all the way at the bottom, no matter what, you're going 4.5 meters per second. Because horizontal velocity doesn't change, apart from with wind resistance, which on small scales, well, which in our course we'll always just neglect. We'll just get rid of it to say it's not ignoring wind resistance and stuff like that. We'll always ignore it. It's not mysterious or anything. It's to do with surface area and density and stuff like that. Like you'll when you're next year at university, if you do anything like this, you will include wind resistance, but it's not even that hard to include. We just tend not to. But anyway, at the bottom, its horizontal speed is definitely 4.5 meters per second. Now, we need to also know its vertical speed. Now, this is a bit harder because, yeah, we don't know. It changes. Now, here's the thing. We can avoid writing suvat because the suvat that we've got here in A is actually the same suvat that we need for D. That's just for the whole jump, the suvat we've done here. So we just need V. So let's pick an equation to get V. How about V equals U plus AT, because that's already got V as the subject. Cool? Using the suvat from A then, here's what you get. V equals U, the initial speed, well 0, plus A, 9.8, and T, 1.43. Which means the speed that we hit the water with is just 9.8 times 1.43, which is 14.0. Okay, so we've got a horizontal speed and a vertical speed. Final thing you do to kill the answer, the final thing you do is just now write them out as vectors, okay, buddies? So to start with, as we hit the water, we've got a speed this way like that, 4.5 meters per second, followed by 14 meters per second down. Okay, and that means our resultant speed, buddies, is this here. How do you get it? Our final speed? Well, Pythagoras' theorem. V equals the square root of 4.5 squared plus 14 squared, which means V is 14.7 meters per second. So the horizontal speed didn't actually add very much. It also wanted to know the direction. The direction is just going to be given by theta, and just go for it. Tan theta is equal to 14 over 4.5. So theta is, shift tan, open bracket, 14 divided by 4.5, 72.1. Okay, so ready? Final answer is just this then, buddies. V equals, and it's going to be 14.7 meters per second, open square bracket, 72.1 degrees, and I'm going to say below horizontal. And that is it. Done and dusted. Cool beans, buddies. So below horizontal because that was horizontal and you're below it. So 72.1 below horizontal, which is quite cool. The horizontal speed didn't play a big role, but the vertical speed massive did. So yeah, it's not like you can just add the two together. It wasn't like 18.5 like you might expect. It was 14.7. The downward speed added way more than the horizontal. So I hope that that's okay. You're just going to get a chance to practice for the rest of this lesson. I hope the video wasn't too long. And here you go. For the rest of this period, have a little go at that. When you're all the way done, just do a mix though, so 110, 1 to 7, but do a mix. When you're all the way done that, my buddies, take a picture, take a single PDF with Office Lens or Cam Scanner, and then upload it onto Google Classroom for me. And that's it for me. See you next time. Bye, buddies!